Hi, in this problem we're going to look at competing exponentials. So we have three exponential random variables, x with parameter lambda, y with parameter mu, and z with parameter nu. And we want to calculate some probability. And the probability that we want to calculate is the probability that x is less than y is less than z. Now, we can reinterpret this as three Poisson processes, because the link between exponentials and Poisson processes is that the interarrival time of Poisson processes are exponentially distributed. So you can think of x being the time until the first arrival in a Poisson process with parameter lambda. And the same thing for y is the first arrival time of a Poisson process with parameter mu. And the same thing for z and nu. And so in that interpretation, x less than y less than z, you can interpret as a race, meaning that x finishes first, followed by y, and then z comes in last. So with that interpretation, let's see if we can calculate what this probability is. We can rewrite this, this probability as a combination of two things occurring. One is that x is less than the minimum of y and z. And then the other is that y is less than z. So what does this first event mean? This first event means that x comes in first. And it doesn't matter whether y comes in second or z comes in second. So we first say that x has to come in first, which means it has to beat the better of y and z. And then that combined with the fact that y does better than z is the same thing as saying that x is first, y is second, and z is third. And now let's try to argue using Poisson processes that these two events are actually independent. So this event occurring means that x is smaller than y and z. So let's take these Poisson processes, and because these random variables are assumed to be independent, these are independent Poisson processes, so we can merge them. So let's merge these two, and we'll get a Poisson process that has rate mu plus nu. And we can also merge this first one and that one, and we'll get another Poisson process with parameter lambda plus mu plus nu. So in that context, what does it mean that x is less than the minimum y and z? It just means that in this merged process, the first arrival came from the x process. In that case, if that's true, then x is less than minimum of y and z. Well, let's say that that event does occur, that the first arrival is from the x process. Now we're interested in whether the second two, what the order of the second two arrivals are. Is it y first and then z, or z first and then y? Well, it doesn't matter because of the fresh start property. Because after this arrival comes, and say it is from the x process, the Poisson processes start anew, and they're still independent. And so what happens after that is independent of what happened here when x arrived. And so whether y came first followed by z, or z came first followed by y, is independent of what happened here. And so because of that, these two events are independent. And so when we have the probability of the intersection of two independent events, we can write that as the product of those two probabilities. Now, what is the probability of this first event? The probability that x is less than the minimum of y and z. Well, we just said that that corresponds to the first arrival in this merge process being from the x process. Well, that probability is lambda over lambda plus mu plus nu. So it's equal to this ratio where the process that you're interested in, its rate comes in the numerator, and then the merged rate is on the denominator. And what about the second one? What's the probability that y is greater than, or y is less than z? Well, let's go now to this merge process where we merge just the y and z processes and see which one comes first. Well, in that case, what we want to know is, in this merge process, what is the probability that the first arrival came from the y process? Well, analogously, that probability is going to be mu over mu plus nu. And that gives us our answer. And so we see that what looked like a pretty complex calculation, when we reinterpret it in terms of Poisson processes, it becomes relatively easy to solve. But this still seems like a complicated expression, so let's try to check to see whether it actually makes sense. So one way to do that is to look at a specific example of the choice of lambda, mu, and nu, and see if it actually makes sense. So one example is, suppose that all three of these parameters are the same. Well, if they're all the same, then this probability, the first part becomes 1 over 3, 1/3. And the second one is 1 over 2. And so if all three parameters are the same, the probability becomes 1/6. And let's see if that makes sense. If all three parameters are the same, that means that these rates, these arrival rates, are all the same. And what that means is that any three ordering of these three arrivals is as likely as any other ordering. And what we're interested in is in the probability of one particular ordering happening, which is x first, then y, then z. But if everything is symmetric, then any of the orderings is as likely as any other one. And how many orderings are there? Well, there's 3 choices for who comes in first, 2 for who comes in second, and 1 for who comes in last. So there's a total of 6 possible orders in which these 3 contestants, if you think of it that way, can finish this race. And out of those, we want the probability that one of those outcomes happens. And so the probability should be 1/6, and that's what our formula tells us. So as I said, in this problem, we saw how to reinterpret exponentials in the context of Poisson processes, and that helped us solve a probability that looked like it was pretty complicated. So I hope that was helpful, and see you next time.